Hi class, welcome to our first microlecture. The topics here are just an intro to organic chemistry and a review of Lewis structures. So let's first discuss what organic really means. It used to be thought that anything that was organic had to come from living matter. It is true to say that these rocks are inorganic material and this plant is organic. But it would be wrong to say that the reason is because the plant is living and the rocks are not. A better definition would be anything that produces carbon upon combustion. There are plenty of examples of non-living things that produce carbon upon combustion. So our preferred definition of organic chemistry is carbon-containing. So the study of carbon-containing compounds, and there are thousands upon thousands of them because carbon forms 4 strong covalent bonds and is very versatile. So carbon is aptly called the king of all elements. On the right, you see a periodic table of all carbon. This is a common joke among organic chemists. We have a few other favorite elements like nitrogen, oxygen, maybe the halogens. Other than that, it's all carbon. So I mentioned nitrogen and oxygen as being favorites. The other most frequently mentioned elements in organic chemistry are hydrogen and phosphorus and sulfur as well. Mainly because these are the elements that make up carbohydrates and proteins and lipids, as well as DNA and RNA. Applications of organic chemistry abound. It's not just about chemicals. It's also about food, textiles, medicines, including vaccines for COVID-19. So without further ado, let's jump into our review and start drawing some valid Lewis structures of organic compounds. Let's do an example here of H2CN2 or diazomethane. So the first thing to do is count up the total number of valence electrons. We remember that hydrogen has a group number of 1, so valence count 1. There's 2 hydrogens. Each has 1 valence electron, and we go on to all of the other elements. Carbon, there's 1 of them. It's group number 4, so it's 4 valence electrons. And then we'll add on nitrogen, there's 2 of them, and nitrogen is group 5, so 5 valence electrons. And so we can easily come up with a total count of 16 valence electrons in this structure. And we want to keep in mind that carbon and nitrogen, anyway, are going to follow strictly the octet rule, which means that there should be 8 electrons total surrounding those atoms. Hydrogen doesn't have to follow that rule because it can only accommodate a total of 2 electrons around it. And so we just start drawing a structure that makes sense with regard to how many atoms we have, the types of atoms, and their number of valence electrons. If I start with this as my connectivity, I see that I've got a total of 2, 4, 6, 8 electrons in the structure. And so I'll go ahead and remove those highlight marks. And so I'm going to count on from that 8 electrons total because we want 16. I'm going to go ahead and just put them in the form of lone pairs. I'll start with peripheral atoms because they tend to be more electron bearing. So I'm going to put 2, 4, 6 non-bonding electrons around the peripheral nitrogen there to give it an octet. And so that was 8 electrons to begin with. 9, 10, 11, 12, 13, 14. We just need 2 more electrons for a total valence count of 16. So I'm going to go ahead and put them on this nitrogen. And now we have to think about whether or not this structure satisfies all of our rules. We can clearly see that carbon has a total of 6 electrons around it. 2, 4, 6. So it's not obeying the octet rule. So this is not a valid Lewis structure. So at this point, we think about rearranging electrons so that we change sigma bonds perhaps into pi bonds. So sigma bonds are single bonds, and pi bonds are either double or triple bonds. And so perhaps these electrons here are actually, I can move them or think about moving them between the carbon and nitrogen to make a double bond there. That would surely make carbon happier because it would have a valence count of 4 and it would have 8 electrons total surrounding it. So let's draw out what we get from just that step, from that maneuver. So we would get this structure, okay? And so, so again, this was not a valid structure. We're just using it to come up with the valid structure. Is this next structure a valid structure that we came up with? Well, no, because nitrogen doesn't have an octet. The one in the middle has 6 electrons total surrounding it, and we want 8 for nitrogen, as we said. So it's in violation, and so let's do that same trick again, where we move the electrons around. We can think about one of those lone pairs on the peripheral nitrogen as being shared, and that would create a pi bond, a double bond between those 2 nitrogens. And so this is the structure then that we would get after that maneuver. Okay. In this structure, all atoms have an octet that need to, so the carbon and nitrogens both have their octets. So this, again, this was not a valid structure, but it looks like this one is a valid structure. And then there was one more possibility, if you thought of it. Okay, so this has 16 valence electrons. All atoms that need to are following the octet rule. And so it is also an acceptable answer. This is our second example, and I'm going to go ahead and go through this one a little bit quicker, but pause the video and try to come up with your own answer first. Alright, so let's draw the Lewis structure for fulminic acid, HCNO. First thing is always to count up the valence electrons real quick. So there's 1 hydrogen at valence 1, there's 1 carbon at valence 4, there's a nitrogen at valence 5, an oxygen with valence 6, and so that's a total of 16 valence electrons. Let's go ahead and draw our connectivity. Here we have only 6 valence electrons showing, so we have to add some non-bonding electrons. I'm going to take the most electronegative atom, which is a peripheral atom, and give it its octet first, and then just kind of distribute 16 electrons total around the other atoms. And we can clearly see that this is in violation of the octet rule. Carbon has 6 electrons around it, and it needs 8. So we're going to rearrange electrons to form some pi bonds. So if I took away the lone pair on carbon, what could we come up with for some valid structures? At this point, carbon still doesn't have an octet. And so, what else could we do? Well, nitrogen has a lone pair. And so theoretically, we could give carbon back its lone pair, and nitrogen could actually double bond with the oxygen. So let's just check and make sure that we still have 16 electrons. So it's 2, 4, 6, 8, 10, 12, 14, 16. We do. Nitrogen has 8 electrons around it. Oxygen has 8 electrons around it. And carbon does as well. So that is a valid Lewis structure. There is one other one, if you were able to come up with it. It is not a very happy structure. Carbon in this case would have 2 lone pairs.